Okay, so I just have a large amount of vocabulary that we're going to go off. We're going to learn in this video. The first thing is we're learning about simple harmonic motion this week. And I want to describe what we mean by simple harmonic. The first part of this is we're definitely going to say that simple is referring to the fact that this is pretty ideal. This is harmonic motion that does not have a lot of the complications that come in more complicated problems. Like, for example, one of the simplifications we're making is we're going to assume that any pendulum that we do is being done at a 10-degree angle or less. It turns out that the angle does have an effect on how long it takes for a pendulum to go back and forth. But as long as you keep the angle below 10 degrees, the effect is pretty minimal. So simple harmonic motion, we will be doing some simplifications like that so that we can look at the harmonic motion without getting bogged down in a lot of details. So simple. The other thing that we're going to be avoiding talking about, I'll talk about a little bit later in the video, which is dampening. The fact that like if you did have a pendulum, in reality, it would go less far and eventually stop. In our perfect simple harmonic motion, it goes forever or it goes for as long as we need it to for the problem. All right, harmonic is referring to the repetition, the repeating nature of this type of motion. We have these things called periods that I'll talk about in just a sec that just repeat over and over and over again. And when we're talking about harmonic, we're describing that behavior. And we're also describing that it can repeat sometimes faster and sometimes slower. And again, looking at why it does that and how the behavior can change when that happens is part of the simple harmonic motion. Finally, the motion is just what it says. We're talking about specifically this repeating motion. Let's get into some of the vocabulary. The first term that I want to talk about is the period. So if I have a pendulum going back and forth, the period is the time it takes for one cycle. And by cycle, we're talking about for it to get back to where it started with like the same velocity vector. So if it's starting from one end and then going back and coming all the way back to where it started, so back and forth or something like that, forth and back, I don't know. When it gets back to where it started, that would be one period. Or if we were talking about starting in the middle and it was going up and then it came back, and then once it was back down here, that would be the start of the period again. Not when it went up and then came right back, because this time it was going the opposite direction than it started. So we have to see the motion repeating for it to be a period. Now, I did this in red because it will help us remember that periods are things that repeat themselves on some kind of a regular cycle. And it's this repetition that makes us call lots of different things periods. So if, a period, again, is the time it takes for one cycle, and that cycle can really describe all kinds of things like, and I know that you guys are a little bit grossed out by this, but school. We have periods that repeat every day, and they're always about the same length, and teachers always do the exact same boring thing. So the time that it takes for one repetition is called a period. Okay, on this graph that I have here, this is a graph showing the motion of either a pendulum or a spring going back and forth. You can see it's going back and forth and back and forth, or it's going back and forth and back and forth, but we're just measuring it along the x-axis. The period would be measured right here from the crest to crest or trough to trough. When we see the cycle start to repeat, if you could copy it and paste it right over and it would just repeat the exact same thing, then you've got a period. And periods are always measured as units of time. And in our class, we use a capital T to represent the period, and we measure it in units of seconds. Now, our next one is frequency. And frequency is exactly the opposite of a period. If a period is the time it takes for one cycle, the frequency is the cycles in 1 second. So if it took 1 second to do a full repetition, the period would be 1 and the frequency would be 1. But if it took 2 seconds to do a single period, then it would only have gotten half of the frequency would be half because it only got half of a full cycle in that 1 second period of time. So mathematically, the formula for frequency is frequency is equal to 1 over time, or 1 over period. So it's the exact opposite, and we measure frequency in units of hertz, which are really just a fancy way of writing 1 over seconds, or seconds to the -1 power. But because biologists are bad at math, we came up with a special unit called hertz, so that they can just use this without thinking about inverse seconds or something scary like that. Okay, so that's frequency. On the graph, you can't really see it, but you can always figure it out by just taking the period and do 1 divided by the period, and that will give us the frequency. Next is our amplitude. When we talk about amplitude, we're talking about how far it moved from the equilibrium position. Man, I did a lot of this vocabulary in the wrong order. How far it moved, let's talk about equilibrium position first. Equilibrium position is the spot it would rest at. Meaning that if we left it alone, or we stopped it and let go, it would hold itself in that position. So a pendulum going back and forth, the side is not an equilibrium position, because if we let go, it would move. This side is not an equilibrium position, because if I let go, it would move. But right in the middle, if I let go, it would stay there, and it would actually be in equilibrium. The force of gravity and the force of tension would be equal. Same thing with an oscillating spring. If I pull a spring back and I let it go, it's going to go. And if I push it in, it's going to go. But if I just leave it at its equilibrium position, it would stay there, because the spring is not stretched or compressed, and the sum of the forces on there would be equal to 0. So going back to amplitude now, amplitude is the difference between the equilibrium position and wherever the maximum or minimum compression or moving the pendulum back and forth is. So it's the distance from where you measure equilibrium to the furthest point it ever gets. So it's the max displacement. And we're going to measure this in distance units. Pretty much it's going to be measured in meters. Although in the case of pendulums, we can kind of talk about an angular displacement or an angular amplitude in the same way that we would talk about a linear displacement. Either way, it works out to be the same idea. On this graph here, the amplitude is right here. That is our amplitude. Sometimes it's called x min, x max. Just be careful. The common mistake that is made is calling this the amplitude, from the very top to the very bottom. But it's from the equilibrium position to the maximum or minimum, not the very top to the very bottom. Okay, next thing that I want to talk about is just a word that you're probably going to come across, sinusoidal. So that just means it's shaped like a sine graph. A sine graph. So you can see that this graph that I have right there is sinusoidal, and anything that is sinusoidal when you graph it is usually some kind of harmonic in some way or another. If we're talking about it being motion, then it would be a harmonic motion. And if it's really ideal and perfectly could match some kind of sine graph, then it's simple harmonic motion. Now, dampening is the fact that in reality, the graph would not look like this. It would look something more like that, and it would lose energy as time passed because it's losing energy from its environment. The only thing that you really have to know about dampening is that it's a loss of energy to the environment, but we don't really talk about it in this class unless there's just a conceptual problem. And if there was, you just say, okay, energy is being lost, and then move on. That's all we really need to do with it. Okay, angular velocity is a weird thing to talk about in this unit. Really, we'll get into it in rotational terms, and when we do rotation, it'll make a lot of sense. In here, angular velocity is a quantity that tends to be useful for a lot of calculations and derivations, but doesn't really make a ton of sense in the unit itself. So I'm not going to dive into angular velocity right now as far as what it really means. We'll do that when we get to rotation. I'm just going to give you a formula that you can use to find angular velocity if you're ever asked to. So the symbol for angular velocity is this Greek letter omega. It's a really curvy W type thing. And if you're trying to solve for it, it would either be 2 pi times the frequency, or the same thing, since we know that frequency is the inverse of period, it could just be 2 pi over period. So if you're asked to find the angular velocity, or you're given it and asked to find frequency or something, this is the equation that you would use. And we'll talk about angular velocity later in another unit. The last thing I want to talk about is the average velocity of something like a pendulum or like an oscillating spring. Now, we can't really describe the velocity super well because the velocity is constantly changing. The pendulum's changing direction and changing speed all the time. Same thing with an oscillating spring. We can't even really talk about its average velocity because truly its average velocity should be zero, because most of the time, it's either going one direction or the other, and if we average it all together, it becomes zero. But if they ask for average velocity or they ask for average speed, what they're really looking for is the magnitude. And in general, there is a way for us to calculate the average velocity magnitude if we're ignoring this whole directional piece, which is a way that they ask these questions. So if you're asked for the average velocity, I want you guys to just remember something that came up on the last exam. Average velocity is specifically the total distance traveled over time, or the displacement over time. So in the case of this spring oscillating or this pendulum oscillating, if we can figure out how far it goes and divide that by a period, that would give us our average velocity. And so one of the things that we could do that with is with this graph right here. Over the course of a full period, you can see that it's traveling from this point here all the way down to there and back up to there, which from the x-axis, from the y-axis, which represents the position, which is x, it's moving down 1x, 2x, and then back up 3, 4x. So if you're ever asked to find the average velocity of one of these sinusoidal simple harmonic motion type things, then what you're really looking for is the average velocity, which is 4 times the amplitude over time. So that's some of the big terms and equations, but I don't even really know if we call these equations. These are more just definitions that you need to have for the rest of the unit. So I hope this all helped, and I will see you guys in class.